Hey everybody, welcome. This is a live program, a live broadcast from Discovery Hall in room 103, the auditorium. And this is a new way to start this whole thing. Nat the Wonder Boy is here. He's put out 7 fires already. We had a thumb drive that was not working, blah, 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 blah. I think we're functional. Thank you for joining us. If you're watching this in replay, it's 11:54 right now, and we will begin this lecture at noon, which is about 6 minutes from now. And after the fact, I'll set a bookmark for the beginning of the actual introductions and then the talk that we have today from Doug McFarland from Tri-Cities, Washington. Looks like we're 5 by 5. Thank you for that report. That means loud and clear. And you can see the room is full of activity. This is our first noon talk of the quarter. Matt, you want me to test like something? No, I haven't. You're right. So there's the face camera. There's the slides in face. There's slides only. There's 2 cams, no big deal. That's all going out on the broadcast, everybody. But the slide is happening here as well. So, yeah, I will turn the loudspeaker. Nat's worried about the speaker. I don't blame you, Nat. I'm weirdly way too comfortable and cocky based on what we just had. So we had people freaking out trying to figure out how this works. We had an encrypted thumb drive, too much information. Where are you viewing from today? Can I say hi to a number of you before we, oh, Nat's really antsy. He's connecting the boom speaker right now. Michael is from Trim, Ireland. Michael, it's great to have you as always, and the family. Say hi to Nee and your lovely wife. Burpengary, Australia. Have a good one. Australia is my new favorite place. Medina, Ohio. Marysville, Washington. Pullman, Washington. Papagino says, hi, Hannah. Philomath, Kirk, hello. Garrett, the Dutch night owl from the Netherlands. It's not projecting yet, right? Oh, we got anthropology. Okay, so
he's gonna have it click on mic, right?
He's got it on. Oh no, he doesn't. He took it off. All right, you got it.
I was almost that guy.
Oh
I
yeah.
turned it off.
Oh, that would have been. Oh, that's a Warner's Brothers special. That's a blooper reel.
Yeah.
Beautiful. Thank you. Okay. So let me ask the home crowd, can you hear our speaker, Doug? Doug, did you break stride? Did you literally run going to the car and back to get that laptop?
I'm not in that kind of shape anymore, but I did. There were intermittent jogging and running stretches.
Okay, very good. Can you hear Doug, please? There's a delay in the comments. Doug, did you go on and get another degree after Central, or did you stop with a bachelor's?
No, I got a master's degree.
Here.
Yeah, you'll see some of that in the presentation
good.
too.
Okay, very good. Viewers, I need a report. Oh, the speaker is 5 by 5. Very good. Okay, so you are all set. We are all set. I am going to turn on the amplifier for the room.
You want me to just hang out up here while you're...
You bet. I think so, yes. And I'm going to stand right up here next to you and introduce you, but it'll be very quick.
Okay, I'm going to go get one more.
That sounds good. Now, right, I use... Watch this, Matt. I'm a well-trained little monkey.
Well, I'm just saying, it's going
to pop.
It's going to have a pop if you don't.
Okay, right. We're a little early. I always put the volume on 0.
Perfect. That can be on.
Okay. So I'm going to wait 2 minutes before we do this. I can turn it on, but I'm not going to start. So I literally kind of try to stay behind and not go in front for feedback and say, how we doing? How we doing? Can you hear me? And I keep cranking until I hear some kind of weird, yeah.
That's it. That's all there is to do, I believe.
I believe I can fly, Nat Nickel. I can believe. Is Monday the deadline?
I think today is.
I haven't heard anything yet.
Nothing means anything.
Okay. You're doing good. I like you, man. You're not flustered by anything.
Oh, not yet anyway. It takes a lot more than that.
Okay. Yeah, I know. You know, we've so leaning into the fact that you've spent time on this campus and you have a couple mentors in the room, and someone said, you know, like this is primarily for our students. This is not so much for our faculty and staff. So
Right.
Don't be shy with that.
Okay.
I think you were going to do some of that anyway. But
Oh yeah, there's some humor in there.
okay, good. I will, once I introduce you, I'll just be sitting right there, and you can just ignore me, talk to the crowd as normal, and we will have, I'll play off your lead. If you want to do a bunch of back and forth during the talk, fine, but if you want to do more of a formal Q&A at the end, I'll change the camera setting and we'll do that.
I'm probably going to make it up as I go.
I love it.
If I look out there and people are like,
yes.
then I'll start asking
Good.
questions and wake them up.
Good, good. Okay. Put your finger right there. Really? How many beats per minute?
Has it been a morning? That's pretty normal. I'm more up. I can find out real fast.
Your hands are like ice.
That's what she always says. I'm cold-blooded, I guess.
Warm heart.
Warm
or
heart.
maybe. Okay. If you're going to be on the fly, I'm going to be on the fly too.
Okay.
Okay?
All right.
This is Evening at the Improv.
I love it.
Good afternoon, everybody. Good afternoon. Hey, everybody, how's it going? Can you hear my voice coming out of the speaker? Yes, thumbs up. Do we need more, Julie? Is that just about right? A little more before we get feedback, something like that. That's pushing it right there, I think. Okay, welcome everybody. It's so great to see you all. Thank you, thank you, thank you for being here. I have a few extra announcements beyond what we normally do because this is our first gathering. So the first thing to say is, welcome back, lots of familiar faces. This is where we get together Fridays at noon. But there's some new faces here as well. So welcome to you. I hope that you feel comfortable. Look around. These are your people now. Come on. These are your people for the next year, 2 years, whatever. So settle in. Enjoy yourselves. This is a department-wide talk, but it's designed for the students. It's designed for the students. And our speaker today went to school here long ago. So he's going to lean into that significantly. I need to do some announcements, though, before we get to our speaker. Standing in the back is Bree McGinnis. She's waving her right arm. She's waving it. Look at that. She has paperwork involving permission to put you on camera or a written form to say, get me off camera. I never want to be on the internet for any reason. So if you're a private person and never want to be put on a camera, you're going to be always sitting in this back corner over here. That's the death zone. That's the quiet zone, the dark zone. We never put you on. But basically, if I make a diagonal between me and Bree right now, everybody to the right, as you're looking at it, it's fair game to put you on camera. You don't see yourself right now, but you are on camera right now going out. There's a couple new wrinkles this year. So please, if you haven't done that little paperwork that's outside the door, you do one form once. It's good for the whole year. But we need that documentation. Eddie, I need your signature on this 101 lab form. We're good. Okay, great. So that's that. See Bree afterwards if you've got a question about that business. I also have your attention, so let me go with another one. We're doing a group photograph, I think. And, yeah, okay, great. So we have someone to, thank God, we have someone to take photos of us as a group. I don't know how that happened, but we managed to make it work. Thanks to those that made that happen. So please stick around after the talk. About 1 o'clock, we're all going to go out to the north side of the building, and we're going to take our group photos. And you're like, why would I do that? Well, you'll be famous, man. You'll be in the hallway on posters on all 3 of the floors. You'll be physically, like, legitimately part of this group for 2025, 2026. And we'll do an undergrad photo, we'll do a grad student's photo, we'll do a, I guess, faculty and staff photo, we'll do an everybody photo. And that's the crowd favorite, of course. I think it's just us. I don't think physics is involved. So it's just us, but we will hustle out there, and Ann's partner will be taking care of the camera work for us. So wonderful. Please stick around for that. 504, do we have to, who's doing that? Do we have to, Bree, now the other hand. Now there's both hands up. What do you want to say to these guys?
If I don't know you, then I can't take you up. So come check it.
Very good. So Geology 504 or 304, and you don't know Bree, please go find her also after class. Anybody got anything else to say before we start here today? Okay. I think I want to switch cameras. This is all new. We had a bit of a cluster F up there as we got started, but I think we're good. So before I get to Doug, and Doug's a low-key guy, so he's rolling with whatever we've got, can I quickly tell you about the other talks that we have lined up for this fall? They're all in October. So next Friday is October 10th. We have a guest from South Dakota, geology professor Trevor Waldine. He's going to be talking about Alaska tectonics. Why is Alaska curved? Tectonic development of the Alaskan orocline. That's a very special talk from a very special young geologist. October 10th. Next Friday, we'll see you all again. Following Friday, October 17th, nothing, GSA and other things going on. Following Friday, October 24th, Mitch Allen from the Washington Geological Survey talking about landslides. He's a co-worker with Jordan Carey. Jordan now works with WGS as well as Central. And another WGS/Central connection between Jordan and Emily Richard on Halloween. Costumes optional for debris flow fire talk from Emily. And that's our 4 talks for the fall quarter, condensed into the month of October. So we'll be at it. We'll be at it. It's like you don't have to say, are we having a talk this Friday? Basically, the answer is yes, once we're in the role in the month of October. Finally, our speaker today is Doug McFarland, and Doug is from Tri-Cities, and Doug was a student here in the mid-1990s. I had Doug in class, Carl Lilquist, some anthropology professors are all here. It's a nice reunion of people who used to be together, learning together here on campus. This building did not exist, but Doug was here. I'm going to let Doug just go for it. This is a archaeology, geology talk. The title, Only the Lonely, Magnetic Analyses of Single Archaeological Burned Rocks to Address Use and Function. Please help me welcome Doug McFarland.
Thanks. It's fun to come back to campus. You'll see that I have an extensive, it's part of my presentation even, I have an extensive relationship with Central for the last 30 years. I want to first say that I'm disappointed that physics isn't here because they could probably tell me something about my presentation that I don't know.
Yeah.
Magnetics is a big deal, right? So who here knows what a rock is? All right, geology is awesome. Who all knows what a magnet is? Okay, good start. So I'm going to combine the two in this talk, and we're going to talk about how the two combine within the archaeological area of investigation, and how geology and archaeology sort of bind together. So before I go into that, I need to thank the Jamestown Skull and Tribe and the Tribal Historic Preservation Office. They were huge in getting me access to the resources for this study and analyses. And you know, it's important for everybody to think about that when you're working in areas where tribes are present. Bring them in, make them part of what you do, because they were here, we're all here together. We need to work together. So, I speak in timelines, you guys speak in timelines. I thought I'd use a timeline to explain my path to this topic. So, my kids tell me that I'm older than dirt, so I used a geological sort of timeline. So the Precambrian was before I knew I was going to be an archaeologist. As the son of a geologist, I listened to lectures my entire youth about this and that, and he was local, so I got to hear about the Columbia River basalts and the coulees and the Missoula floods and on and on. And I tried to ignore most of that, to be honest. As a young adult, let's just say we all understand the lost years. No need for me to expand on that. I was a non-traditional student, came back when I was 24 after finding some solutions to some of my own challenges. But during that, I had my father step in and say, you already know about geology, why don't you help me do geophysical surveys? And I'm like, what's that? And so he explained to me the use of different energies on Earth materials for identifying a broad spectrum of things. So once I decided to step back into the world of school, as a bachelor, I hope there's no English majors in here. I came in as an English major, realized that wasn't my path, and went to geology and had people say, oh, you kind of already know some of this stuff. And I was like, yeah, but to me, sitting in a classroom was like listening to my dad lecture, so I had dad trauma and was not able to deal with that, I think. So then I was hooked by a professor who is no longer teaching here at the university. Dr. Bill Smith was huge in getting me into archaeology. Pat McCutcheon, who is here, was a big part of my path. And Steve Hackenberger also was a big part of my path. So as a team, they guided me into what I thought was going to be a trip to the exotic areas around the world and finding treasures. Well, that's not what archaeology is, it turns out. So I realized, mostly by information from my mentors, yeah, you really need to get a master's degree if you're going to do anything with this archaeology, this anthropology degree. So then I was like, okay, all right, I guess I'll go back to school. And I'm not going to talk too long about the timeline, but everybody here knows about how long a master's degree is supposed to last, right? Okay, just checking. So I got this brilliant idea. Hey, I know a little bit about geophysics from working with my dad. I'm learning about archaeology, and some of the stuff that we're looking at is in the earth. Why don't I come up with this brilliant new idea where we use geophysics to find archaeology? So I started down that path and realized that path had been discovered before I was born. So it was interesting to follow everybody's path, though. So that led to me eventually getting a job when I left the world of academia with Pacific Northwest National Laboratory. Now, between leaving academia and jumping into the lab, I worked for archaeological contracting work. And for those of you who don't know, archaeology isn't always about going and finding cool stuff. A lot of it, most of the archaeology is actually done by compliance archaeologists who the law requires them to go look in areas before there's development that includes state funds, federal permitting, federal land, state land. We got to go look and check stuff out, make sure there's nothing there. So, getting back to the lab, it was an awesome, amazing environment. I combined more my information and knowledge with geophysics and geology with archaeology, which is actually a subfield of archaeology called geoarchaeology. Did compliance archaeology while I was there as well. Applied science, we would go do cool stuff. Things that we thought up, we would go test them, experiment, and research and development, which is you come up with an idea and you got to try to sell it to someone with a lot of money. That's hard work, by the way. So going through that path in the last couple of years, I had an opportunity to make a more formal reconnection with Central. Pacific Northwest National Laboratory has a program called the Joint Appointment Program, and it's like they talk to universities and like, hey, we'll loan you our scientist, but you got to pay us, you know, to loan them to you. So I'm kind of on loan to CWU right now, but since I left academia, I've been in touch with Central up until the present day, collaborations, and you know, having them come in on proposals that I'm writing. They have me coming in on stuff that they're doing, so it's been a great relationship. So as you can see, I am a wildcat through and through. There is no other school for me. So that leaves us off at today. As you can see, the little red triangle there is that's like my symbol for magnetics. It's basically the magnetic fields, north and south poles. That is where my interest in magnetics sort of gelled, and it's taken me all the way through today. It's a very interesting topic for me. So fire-cracked rock, right? We saw a picture of a rock in the beginning. It had been fired and cracked, so it's fire-cracked rock. But who cares? So what is fire-cracked rock? It's rock that's burned through intentional use of fire. And we're going to put parameters on that because you could add a lot of things to that, but it might be wrong. This rock can be found globally. I mean, humans and pre-humans have been using fire for millions of years. So almost anywhere you've had people, you're going to find probably fire-cracked rock. I think it could actually tell us something about our relationship with fire, which is a really long relationship. And it's changed. Even before the Industrial Revolution, there was a lot of changes in how we use fire, what do we do with fire. Stones have been with fire for a long time as part of that journey. And it can help us define the landscapes that we are currently living in. You know, the people who lived here before us, what we do here now, anyone who goes camping or hunting, they all use fire. You can look at a landscape, look at the fire-cracked rock across that landscape and what it symbolizes, and actually learn something about the landscape itself. So here's where we kind of bring it more specifically into archaeology. What you see here are some profile pictures of different kinds of archaeological features where the rocks are used as heat sinks. They absorb the heat from the fire, and they re-emit the heat from the fire, and they serve lots of different purposes. So unfortunately, as archaeologists, we destroy what we study most of the time. If you're excavating, you're destroying what you're actually interested in the process. And these are non-renewable resources. Once you destroy a fire pit like that, it's gone. And it's a record of an activity from the past, but it's still important to people in the present, and that's something that we need to remember too. The tribes still go out and they do activities in these areas where you'll find fire-cracked rock. So these areas are still important for their use, and they still use fire to do some of the things they do, and that fire is associated with rock. So we can look at the record of use of fire up through time. Because archaeology is destructive, I feel like we need to move towards conservation and maximize data potential by looking at specifically small things that we don't have to destroy entire features for. So a feature is a collection of things put together in the past that if you were to move it someplace else, it would not be the same. So a fire pit, you know, that cool fire pit, anything that someone built intentionally, if you try to move it, it's not going to be the same. That's a feature. It's going to be, you know, challenging for me. If you guys don't know what I'm saying because you're geologists and not archaeologists, realize that most of my public speaking is to archaeologists at conferences. So shoot up your hand if I'm jumping way over the top, and I'll stop and address your question. But we will have questions at the end too. Depends on how patient you are. I'm not patient, so I'm always the one to go, I don't get it. So feel free. So who burns rocks? I kind of addressed this already. Yes, in the back.
I already have a question.
Okay,
Could you tell us more about salvage archaeology?
sure. Salvage archaeology is when you know something's going to happen. So there's a formal process that I could go on and on for way too long, and everybody would be asleep by the time I finished. But let's just say that when you are going to build something someplace and you can't build it anywhere else, we want to get as much information as we can out of what is there, because it's going to be destroyed as part of the construction. So we do data recovery, and data recovery is exactly what it sounds like. We try to carefully excavate and find things that could tell us about what we're seeing there. What were the people doing? How were they doing it? You know, how old is this? How long ago did this happen? You know, and as an archaeologist, my idea of old is a lot different than yours as geologists, but it's still pretty cool. Does that answer the question? Okay, perfect. So this guy that I've got circled right here, Homo erectus, this table is a little out to date. They've changed some of these timelines, but it's still pretty close. But what I want to know is, how can a guy who figured out how to make fire not figure out pants? You know, and even up and beyond, it's like, come on, there was pants, you know, 120,000 years ago. I'm hoping. Anyway, so a lot of these things that I'm showing up, I've got websites down here because I'm trying to give them credit for what they did. So if you have anything that you're interested in seeing, you know, take a picture of the address, and you can get to it that way. So back 2 million years ago, we've all been burning rocks, right? So the bad news and the good news. Usually you say good news and bad news, but I found out on the internet, and we all know everything on the internet is true, that artificial intelligence has uncovered a hearth, which is like a cooking fire pit type thing that is 1 million years old. Artificial intelligence. Imagine that. So since I'm out of a job as being an archaeologist, I'm going to have to find something new to do. I'm really good with a shovel. Anyone needs a fence put in, let me know. I can put your fence poles in. Human ancestors have been cooking at this site for 1 million years, is what the internet said. And I actually did look at it, and it looks like a legit article to some degree. They do jump to some conclusions, and they kind of overlook something, and finding it is kind of, they used lab analysis to look at curated artifacts to identify some stuff, so it wasn't like AI was out there digging a hole and finding this campfire. So the good thing is there's no shortage of data. If you look back 1 million years, we can track what was done with fire 1 million years ago, if only we had a way to get that data out of the rocks. So we look at this picture. The site may be 1 million years old, but I'm positive that this photo is from the 70s. I mean, how many afros can you fit in one photograph? So, 1 million years ago up to the present, what you see on the left, that would be your left, right? Yeah, okay, just making sure, is a cooking feature from the Jamestown Sklallam picnic area. And they still use this process to cook their clams, to do clam bakes for their traditional food ceremonies. And that was 6 YBP, so 6 years before present. So fairly recent. This other catastrophe is my sons and my attempt at campfire and hot rock cooking on a camp trip that we did. The egg cooked okay, but there was some grit from where it was kind of sticking to the rock. So we chose not to eat it, but I could see if you're really hungry, you might want to eat it. And this is a cutout from that previous picture that showed all the different archaeological features in profile. So we tried to sort of replicate that to some degree, and it worked pretty good. So it's still used, some successfully, more so than others. So this is one of the coolest things I saw on the internet was stone boiling. And I put this picture up here for a couple reasons. When we're looking at fire-cracked rock, which is what archaeologists call it, and it's not always cracked, and it's not always been directly into the fire. That's why there's like 13 different names for it, but I'm gonna stick with fire-cracked rock because it's what I learned when I was in school. So there's intentional and inadvertent heating. If you look at the picture, the round stones in the center there are being heated intentionally. They're being heated so that they can be put in the bucket of water to boil the water. But if you look at the flat stones around the outside and on the bottom, those are basically being inadvertently heating. They're not heating those rocks on purpose, but it is part of their process that they are using to heat and cook. So there's two ways that you can look at fire-cracked rock. There's going to be the stuff that's heated intentionally and the stuff that's heated inadvertently. And my guess is you go back far enough, most of the heating is going to be inadvertent heating from campfires. People aren't going to be using stones a lot until they figure out how to do that. So why magnetic analysis? So this goes down into why we're talking about this. You know, you have extreme heat in iron-bearing minerals, you get some really interesting magnetic results. And there are lots of ways that you can look at this. There's all kinds of equipment, and I have a slide. It's not in the formal presentation, but it's in my backups that I can show you all kinds of equipment that they use to look at the magnetics of lithology from different types of, not just iron-bearing, there's other magnetic minerals out there besides iron. But lots of information there for us to extract. So what makes a good specimen? So, I mean, you look at the rock, right? You see what we're going to call the cortex. The outside of the rock is red. Well, it's red for two reasons. It's red because there's iron in the rock, and it's red because the heat oxidized that iron and made it red. So when I'm looking for samples, I'm going out and I'm looking for red rocks, right? Another thing that's important to look for is the color of the rock. And you guys are going to learn all about this in your mineralogy classes and lab classes. I still remember some of the stuff that Nick taught me 30 years ago. So the dark color is usually associated with iron content. Iron minerals are usually dark colored. So when I'm looking for a specimen for magnetic analysis, iron content is priority one. Igneous is good for a couple reasons, but one of them is usually because it has more iron than the rest. Sedimentary is pretty good. Metamorphic depends on, you know, if you've got a lot of silicates in your metamorphic rock, or if you have an iron-rich metamorphic rock. And I haven't gone deep enough into this study yet to see exactly. I haven't compared. I'm just looking for what is going to give us good information, because this is a pilot study. This is stuff that's not really being talked about, and so I'm interested in finding out more about it. So thermoremnant magnetism is basically what I was just talking about. It's you add heat, extreme heat, to iron-bearing rocks, and you get induced magnetism at different levels. Now there's a bunch of different things that you can look at and a bunch of different kinds of data that you can get to by using magnetic analyses like this. But they all require a low geological background, which we don't have here. We've got basalts, we've got andesites, all that stuff is really close to the surface. So we can't do anything like surface collected magnetic data. There's a lot of noise that we're dealing with. And you also need an intact archaeological feature. So intact means it's pretty much the way that people left it after they used it and abandoned it. Time takes its toll, erosion, the features get destroyed. It's hard to find intact features without actually using geophysics to find them in some ways. So the top photo here is what we normally find when we find firecrack rock. It's a scatter. We don't know what it used to look like. There could be no remnants of the actual feature left. Nature's taken its course and scattered the rock that was used for whatever purpose across the immediate landscape. So we don't know, it could have come from any one of these four, right? So what if we could sample these rocks? Take small samples of the rocks and do something with them. That is what I am heading towards. So this whole study is a method study, a proof of concept, to see if we can use established geomagnetic and paleomagnetic analyses to extract use information from these heat sink rocks. So what is use? You heat a rock up in a fire, and after you move it and it starts cooling, everything during that cooling process is use. If you're taking it from the fire, putting it in a bucket of water, that's use. If you're taking it from the fire, putting it in a pit to heat something in the pit, cook something in the pit, that's use as well. So the hypothesis is, yeah, we can use these techniques and get information from them. So being a big fan of the scientific method, I broke my hypotheses out into, the alternate hypothesis, which is the one that I want to see, and the null hypothesis, which is the polar opposite. So we've broken our path into two routes. I think that this is how life should be approached. It makes things simple when you break things into yes, no, and then you take this and you go yes, no. So I'm in the first step. So I made it pretty simple. I'm just looking for a parallelism between the number of magnetic signatures in a rock and how many times it's been moved or reheated. Igneous because of the reasons that I already stated. Any questions? Okay. So this is one of my favorite slides because it encompasses like the key parts of what I'm talking about. So what you see in the lower, I should be able to do this, why is it so complicated? Left-hand corner is a model. It's a magnetic model of a stack of rocks. And I used a random number generator to generate inclination, declination, and intensity, which are all magnetic terms. And anyone who is going to be doing field geology or archaeology should know at least about declination, right? It's the difference between true north and magnetic north. So the field that you see in the magnet picture there, the Earth's field has an inclination and a declination and an intensity. And so I looked at what those are for parameters, with intensity anyway, for different types of lithology, and random number generator, hit the button, and it gave me a bunch. And then I did the same thing for inclination and declination, trying to like recreate in the modeling environment a forward model that shows what a bunch of random rocks stacked together would look like. So what you see with the red and the green and the blue in that same lower left-hand corner is what magnetic surface data would look like. If you collected magnetic data over the top of that, that's what it would look like. So if you go directly above that, that's the randomly oriented stack of rocks. You can see the soil has magnetism pointed in all directions, the rocks have magnetism pointed in all directions, igneous and sedimentary represented there. So you get to a certain temperature in the heating process, and that's called the blocking and unblocking temperature. And what happens at that point is all those tiny magnetic fields associated with tiny magnetic particles and crystals, they randomize. And they point in every direction. And then when you reach the Curie temperature, the magnetic fields go away, they vanish. And as the rocks start to cool, between the Curie temperature and the blocking and unblocking temperature, because they're the same temperature for any mineral, and that's going to be an important point. Once you reach that blocking temperature, then all of those tiny magnetic particles reorient in the direction of the Earth's current magnetic field, or whatever magnetic field that Earth material is in. And once you've done that, then you get something like what you have in the lower right-hand corner. And that's magnetic data from an actual fire-cracked rock feature that I found when I was out doing field work. So it has a pole, it has two poles, has a north pole and a south pole. And the reason, I've had people ask me this, so I'm going to preemptively strike here. You see that the south pole is pointed north in this figure, right? Everybody see that? It's because magnets attract on opposite poles. So if you have two magnets together and you try to put the positive poles together, the north poles together, they push apart. But if you flip it, it attracts. So when you have a burn feature in the ground and it's reached the temperature where you're realigning all the magnetics, you have your south pole pointing north and your north pole pointing south. And for some reason, that took me a long time to wrap my brain around until I started thinking about magnets themselves. Okay, so that is thermal remnant magnetism, heat remaining magnetism. So now we're going to talk about partial thermal remnant magnetism. This is where the content starts to get a little more complex. So thermal remnant magnetism, which is that curve you saw, you know, the minerals sort of scatter, then they demagnetize and then remagnetize. That is specific to individual minerals. And so you could have 3 minerals that have different Curie temperatures in the same rock. In addition to having the minerals have their own separate thermal remnant magnetization, the grain size of the same mineral changes, as does the geometry, can change the thermal remnant magnetism. Like the Curie point of that mineral changes with the size of the particle and the mineral and the shape. So you have the potential to have all these different magnetic orientations in one rock. So in theory, like if a rock is used and moved, you rotate that rock within the same magnetic field, you have different orientations at a different temperature as the rock cools. So you have the potential to have multiple accumulating magnetisms. And all these together come together and point out the rock's magnetic vector. So the rock itself will have a north and a south pole, but those are combined, that north and south pole are the results of all of these other magnetic orientations being put together. So movement during cooling can add these different orientations. So can reuse. Like if you use, like in the clam bake pit there, if you use that fire and those rocks to cook your clams, and then you want to take all the broken rocks out because they don't hold heat the same way that an intact whole round rock does. Thermal mass, I don't know if any physics guys in here, thermal mass comes into play with that. Big round rock, less surface area, more internal mass. Anyway, I diverge. So reuse, you take out the broken rocks, the other rocks shift, and you reheat it or you burn it in a different part of the fire. Then you've got stuff that's not heated the same over here, temperature's different. Lots of ways that you can have these different orientations. So the way that we find those is by looking at the rock's total vector and demagnetizing these in stepped heated fashions. So you heat the rock to 100 degrees Celsius, there's a mineral or particle size or whatever that maybe it acquired a separate orientation somewhere between 0 and that temperature. By heating it up to that temperature, you remove it because you've surpassed the blocking temperature. Then you measure the rock's vector in an instrument that does not have an external magnetic field. It protects the rock core from the magnetic field, so you're just measuring the vector of the core. Then you take it up another step and you remove another one of these, we'll call them mineral vectors, and so on and so forth until you get up to 770 degrees when all of your magnetic material has been demagnetized due to that curve process that I showed you before. So it took me a long time to really understand this, so I am open to questions now or at the end, because I know that it's not really straightforward. Okay, I'll move on. So what can it tell us? And I've kind of been talking up to this. Theoretical use moves. So if you look at the 0 use moves, that's a campfire. You light the fire goes out, the rocks stay there. You may have heated it up to the temperature where you've remagnetized everything, but that's just going to be the one magnetic component signature in the rock. One use move could give you two vectors. You heat up the rocks, and then you want to use the rocks and you cook to cook your food. So you take the hot rocks and you move them into the pit. So between the firing and the moving, you've got one magnetic signature. And then once you put it in the pit and it's cooking, it's in a different orientation than it was when it was heated. That's two. So you go to the next one, it's just another, you just add another step to the process. So what you should be able to do, this is my thoughts, is you should be able to look at the number of magnetic signatures, components, individual vectors when you're demagnetizing the rock and eliminate how it was used. Like if you see a fire-cracked rock and you do this analysis and you've got one signature, you know it probably wasn't moved. It may not have been used twice. And there's nuances to this as well, because you can overprint with your magnetic signature. You know, if you have one burn that's at 250 degrees Celsius and then the next one is at 400 degrees Celsius, it erases the 250 degrees Celsius signature. So it has to be under the right circumstances. So this is what the data looks like. And with any science, there's always a little bit of art, you know? So my scribbly lines are my interpretation of the data. Normally, you don't have the colored lines there. The colored lines are supposed to represent data trends. And this isn't a statistical analysis. This is a dougistical analysis. I looked at it like, here's a straight line, drew a line. So what you see here are three different kinds of ways to plot the data. Plot one is just the intensity, the magnetic intensity, which as you see the temperature increases, your magnetic intensity decreases. Plot two is a way to plot both the inclination and declination. I don't like that plot myself because it's pretty messy, and it's hard to see sometimes where to split the data. I like plot three because it shows inclination and declination together combined, and you can see definitive data groupings. So this is how the data looks when you're interpreting it. Okay, so let's go back to the clam bake feature. So after talking to the traditional food group from the Jamestown Clallam tribe, this is the process they described for cooking. So build a fire, take the wood off the fire, put food on the hot rocks, cover the food packets with dirt, cook it, take the dirt off, remove the food, and then you've got the rocks there. So the rocks haven't moved, but I also got confirmation that it had been used multiple times over the past couple of years. So we have an opportunity for reuse. So multiple uses should also show multiple signatures, especially if those rocks were moved or reoriented. So the data that I'm comparing it to is from a midden, which is an archaeological feature that's basically an ancient garbage pit. So they dump all their garbage in one place, and you've got all kinds of stuff in there: animal bone, fire-cracked rock, shells, all kinds of organic stuff. But the thing that made this interesting to me was this archaeological site is associated with the Jamestown Column tribe, and we don't know where this rock came from. It was in the midden, so they did a cleaning. Broken rock, you want to get rid of it because it's not a good heat sink. They took the broken rock, threw it in the midden. What was it? We don't know. So I wanted to compare this, the unknown from 600 years ago, to what we know that they do in the present. Again, this is just pictures of the excavation, the feature, and some of the samples that we used. We do drill them out. There's 1-inch cores that we drill out with non-magnetic drills, because you can induce magnetism in a whole bunch of different ways. One of the ways that I think we're finding out is if you take your material that's not fire-cracked rock from a quarry where they did blasting, the blast shock waves can induce a secondary magnetism. And we're finding that out, and not a geologist. So I was confused when we, in another part of this is phase 1 of a larger project. Phase 2, we found out, oh, there's unburned rock and it has 2 magnetic components. Who knew? So Zach Allen was one of the people, and he's a central student, or was a central student, still in the region. I think he might be over on the west side. But he's the one who drilled out the samples, took them over to Dr. Mike Valentine at the University of Puget Sound, and together they ran the samples, and Mike interpreted the data. So these are the preliminary results from only one sample. This is a pilot study, so we haven't done statistical vigor on this. I just wanted to see if it would work. So the Jamestown Slalom picnic area, we got 2 definitive signatures. To me, that makes sense. Multiple use, cleaning out the rocks. That was before I knew about blasting, but I don't think any of these rounded rocks that they're collecting are from blasting. And the preliminary results from the archaeological fire-cracked rock has 3 components. So what does that mean? We don't know. When you test a hypothesis, you usually come out with more questions than answers. And it just guides you to the next set of questions is all it does. So the next set of questions, well, let's talk about the hypotheses first. I get excited about the next set of questions, obviously. So we rejected the null hypothesis because there is a parallelism. Multiple uses, multiple signatures. So we reject the null hypothesis in favor of the alternate hypothesis. So all the questions that this has generated, for me anyway, are numerous. So experimental archaeology, there's a bunch of really cool shows that you can watch. They're streamed now, of course. But experimental archaeology is where archaeologists try to replicate something that they're finding in the archaeological record by doing something and then coming out with the end result. So my idea was we're going to replicate some of these burning processes and see if we can get the same results that we get from the archaeological material and from the clambake feature material. And then we'll compare them across all 3. But the best way to do this, I'll talk about that in just a sec. I was really proud of my graphic, so I just had to show you that. So we did design an experiment, and we have burned the rocks, and we had, all of the rocks had counterparts that are unburned. So we were able to combine one movement and two movements within one feature, and we had thermocouples in each rock that we were going to be sampling, so we know how hot that rock would get. And then we could test this thermal demagnetization, because that's also supposed to give you the burn temperature of the rock, right? If you see that a component goes away at that temperature, you actually had the rock reach that temperature. So this is the next step. We've completed the burn a long time ago. We're waiting for the data. I'm excited to see the data. This was a big collaboration with Western Washington University, University of Puget Sound. Central was involved. The tribe was involved. So there's a lot of people who were involved, and I know many of them are interested in seeing the results. So I'm looking forward to moving forward with that. That's it. Thank you.
Thank you. We've got just a few minutes for a few questions for Doug, and then we'll go on to our group photos. Who's got a question? And maybe Doug can repeat your question for the home crowd.
So when rocks are magnetized, like igneous rocks, I always think of little, hematite needles lining up or something. How does a rock that doesn't melt reorient? Does it like the spin of the iron atoms or something, or what?
Well, that's more of a physics question. Let me repeat the question.
Thank you.
But I understand you asking, how do the magnetic grains reorient through this heating process? It's not the material itself, but the magnetic fields that reorient. So the magnetic grain itself still has the same orientation, but the field is what rotates or changes and vanishes and comes back. So it's like if you there used to be this, I love magnets, which is part of why I got to this point. But there used to be this thing you could do with a screwdriver where you would point it north and hit it with a magnet or something like that, and the screwdriver would take on magnetism. So the screwdriver doesn't change shape, but the fields around the iron-bearing minerals in the screwdriver do orient the same way. And that's because of the secondary component that I was talking about, which is a shock wave. I wish I knew more about physics. I shied away from physics my entire life, so now I wish I knew about it. So that's an important thing, students. You may not be interested right now in something that you will wish you had the tenacity to push yourself through when you're older than dirt.
Chris?
So the question was, what controls do we have to make sure that we're seeing what we think we're seeing? Like we're seeing a stone boil and not a campfire. Did I get that right?
Yeah, because rather a disturbed campfire. So imagine a cow walked by the last 2,000 years and knocked over what was a campfire. And now, because you've got a use out of that, because now the rocks have reoriented physically, the magnetic fields haven't necessarily changed. Or when you put them into the lab, collect them orientedly, it might look like there's a different field there than there was.
Okay, so 2 points to answer that. The first is that by looking at the disturbed rock, like that scatter that I showed early on in the slideshow, we don't need to have the rocks in their original orientation within the magnetic field to make these determinations. That you do have to have that for like paleomagnetic dating, because they look at where the poles are and they create a curve, and then you use that orientation in the ground, and you match the curve and get a date. But for this, you're just looking at number of moves during cooling. So that would be when you're using it. So if it's already been used and sitting there for 2,000 years and a cow walks by and kicked it, then that isn't going to be represented in the magnetics of the rock, because it only changes, you only add components as the rock is cooling. But I think the best part of that question goes back to the use of scientific method. I'm not trying to prove anything. I'm trying to disprove things. And so by looking at what is possible with one use move, right? If we lay out all the possibilities, campfire, forest fire, because rocks burn naturally, right? This is a challenge that we have to address still. And I can talk to that if someone's interested in it. But you just lay out, and I've already kind of started doing this, tables for 0-use moves, 1-use move, 2-use moves. So if you see 3-use moves, you can eliminate the 1 and 2-use moves and the 0-use moves. And then you look at all the things that are possible with 3-use moves. But we're still early on, and there are challenges. Like I said, this is a pilot study, and it's basically a test case. Is this going to work? So we have more work to do. That's a great question, though.
One more, Chris?
Doug, I was wondering, do you see in the archaeological record or even in the more modern news record, is there preferential, or particular rock types that get preferentially used for this because they better withstand these repeated heating and cooling cycles and don't break down as rapidly? Like, do you see patterns there?
There are people who study that. I think that's a challenging question to ask because it's dictated by what you have around you. I see a lot of quartzite where I'm at be used for firecracked rock, and this doesn't make any sense to me because it doesn't contain a lot of iron, enough to get an oxidized core, but I don't think the instruments would pick up any magnetism. But they're everywhere. Quartzite rocks are everywhere because of the Missoula floods down where I'm at. And so, I don't know. That's a great question. But it's beyond where my brain has gone. I'm like, find the red cortex, find the dark interior. That's the answer.
Hey, let's thank Doug one more time. Thanks everybody for coming today. We'll see you next Friday. And you know what's happening right now. Follow the herd. We're going outside to the north. Group photos. Thank you.
Did I
Great
hit the
job.
time mark?
Perfect.
Oh, good.
Perfect. It's like that was the plan all along.
Yeah.
You know?
See, I told you there was a reason. Oh, thank you. Thank you.
Yes.
Yeah. Well, I don't have Gotcha. And I think I'm going to be. Is Carl going to be hanging around after the picture?
Yes, he
Okay.
is. Carl's not going to be in the pictures, so I think Carl's your man while we're out there screwing around with the photos. Yeah, thanks. Thanks, everybody. I'm going to say goodbye pretty quickly here today because you heard we're all going to do a photo session for the entire geology group. I hope you enjoyed this first talk back after a very long break, and please tune in a week from now, Friday, October 10th. Trevor Waldine will be speaking on Alaska, the Alaska orocline. That's sure to be an excellent talk. Have a good week. We'll see you next Friday. Goodbye from Ellensburg, Washington, USA.
No.